Okay, Chem draw and homework 2 problems. I see that it's a much bigger issue than I was led to believe by the McGraw-Hill people. So a fair number of you, probably almost a quarter of you, are having problems with that. So what I've decided to do for this homework assignment, if you will please submit something, complete the problems that don't require the Chem draw, and don't worry about the ones that do. What I'm going to do for this assignment is just give everyone full credit who attempted to do all the other problems. So you will see probably later this week in the Blackboard grades after you've submitted that homework. And I think you should be able to do the problems even though you don't have the plugin. Is that correct? Has anyone tried to do that? Okay, do the problems that don't require the plugin and submit whatever you have. And for this one, I'll just change then the Blackboard grade to reflect credit for everyone who's trying to do it. So from now on until I can figure out how to get the plugin installed on the campus computers or somehow make access available, what I'll do is use the Learn Smart modules, which I've also put one up for Chapter 3 now. And any homework assignments, I'll choose problems that don't require Chem draw. So any new homework problems shouldn't have that unless I can find a way to get Chem draw on some publicly accessible computer somewhere. All right, so anybody have any questions about the homework? That's going to be done tonight, so if you've started it or haven't done anything on it yet, make sure you get something in on it tonight, because automatically at 11 it'll push everything to Blackboard for me. All right? Okay. Let's continue talking about conformations of alkanes. Remember last time we were talking about the fact that when you have organic molecules with single bonds between the atoms, then the atoms on either end of any single bond are rapidly rotating. And we're looking at how to analyze the structures as if they were frozen in time. And we can see that as you change the rotation of bonds, that changes the interaction of groups on either end of that bond. And so you have different energetic issues involved. And just to remind you of a couple of definitions, we refer to those different rotational isomers as if they were frozen as conformations or conformers of the molecule. And how we look at it, we call conformational analysis. And it's important to be able to visualize the three-dimensionality of these molecules. So we looked at a couple of ways in which we try to represent that on paper. So remember, we can draw it as a sawhorse picture. And in many cases, when we draw organic molecules, the way we represent the bonds with single lines or bold and dash gives us some perspective for the three-dimensional structure. But we also were able to take a look at this, what's referred to as a Newman projection, to visualize the molecule looking down a bond between two atoms. So superimposing or overlapping one carbon behind and one carbon in front, right? So this CC bond, you can visualize looking straight down that where you have a carbon in front with 3 hydrogens on it and a carbon in back with 3 hydrogens on it. And as we look at how that bond between the two carbons we're specifically analyzing, we can see the relationship between the hydrogens on the front and the hydrogens on the back. Okay? That's referred to as a Newman projection. And so you can see that as we look at each of those conformations which are frozen in time, there would be different energetics associated with the relationship between the hydrogens in front and back. And so if we have the bonds on the front and the bonds on the back as far apart as possible, that would be in this staggered position or conformation, where the bond alignment from the front is 60 degrees from the bond alignment in the back. Okay? And that's the max it could be as far apart as possible. So that you would expect, if you were to look at the energy of the molecule in that frozen conformation, to be the lowest possible energy. Right? And that's reflected here on this energy graph. That would be this position right down here. Okay? Then as you rotate one carbon relative to the other, those hydrogens and the bonds start to get closer together until you reach a maximum energy point, where the bonds are 0 degrees apart or eclipsing each other. We refer to that as the eclipsed conformation. And in ethane, that eclipsed conformation is higher in energy by about 3 kilocalories per mole. Okay? So this picture, this staggered picture, represents this lowest energy path position. The eclipsed represents this highest energy position. And then as you continue around a full circle of rotation, since we're talking about ethane and all three groups are the same on the front to the back, there is no difference then as you continue rotating this around until it gets to be staggered. That's going to have the same energy as what we started with. And so that's what you see here. This staggered position is also reflected here on the energy graph and then here on the energy graph. And then once you get 360 degrees, you're all the way back at the beginning. Okay? Likewise, for the highest energy positions, each of those peaks on this energy graph represent the fully eclipsed. There are an infinite number of conformations in that rotation, right? We're just representing the highest and lowest energies here. But if you go anywhere along, say if that's a 30 degrees difference between those hydrogens, you're somewhere here on the graph. Okay? So your energy, you're starting to come closer. Okay? Does anyone have trouble seeing that and visualizing what we're talking about here in terms of these conformations of ethane as the molecule rotates? Nobody? Don't want to admit it? Okay, good. Do you remember what we call that relationship then, or the strain energy for that? The staggered and eclipsed, particularly eclipsed. We refer to the energy that's increased in that molecule as the torsional strain. Okay, in ethane, hydrogens are very small. There are two aspects to those changing energies as those molecules, as the ends of the molecule interact. One is the steric strain, which is introduced when you have large groups bumping into each other. And when we look at more closely molecules that have things other than hydrogen, we'll see that that has some influence on that as well. But mostly in ethane, that difference in energy is related to the electron repulsion from the bond in front to the bond in back. And so as they come closer together, right, there's more electron repulsion, the energy of the molecule goes up. That's referred to as torsional strain. Okay, and we were just looking at this at the end of the last class. So if we take a look at a larger molecule, like butane, now we have 3 sigma bonds in the molecule between carbons, right? We have a sigma bond between the carbon 1 and carbon 2. We have a sigma bond between carbon 2 and carbon 3, and we have a sigma bond between carbon 3 and carbon 4. But what I want to focus on and take a look at specifically is the rotation about this bond between carbon 2 and carbon 3. Okay? You can analyze the others too, but in that case, one carbon would have all 3 of the same groups. And so you can also look at that, but keep in mind, if we're looking at this bond specifically and analyzing the rotation about that one, these other bonds are also rapidly rotating all at the same time. When we look at the conformational analysis for butane, we're focusing on that bond here. Okay, so if I look at this, when I've drawn the sawhorse picture here, and you can see a stick model of that below, I have placed the methyl group that's on the front carbon, the carbon 1 and carbon 4, okay, on opposite ends, right? I've positioned them in this staggered conformation 180 degrees apart. Okay, we refer to that in butane now, where we have not all the same groups on the front carbon and the back carbon. So we have a CH3 and 2 hydrogens on the front, and a CH3 and 2 hydrogens on the back. So not all the positions are equal anymore. When the two large groups are as far apart as possible in the staggered conformation, we would expect this to be the lowest amount of energy for both torsional strain and the steric strain. And we refer to this as the anti-conformation because those groups are 180 degrees apart. Okay, those are anti or opposite to each other. So these stick figures below kind of give you the same view of the sawhorse view, and then if you were to imagine looking down that bond in the Newman projection, this is what you would see in the Newman projection. This is actually a better model of it. So there's your Newman projection. So hopefully that gives you a little bit better view of those molecules. Now, let's take a look actually at this in motion. It gives a little bit better picture as well. So you can see how these bonds are aligned here. This is a space-filling model, and this is the stick figure that you saw before. Notice the anti-arrangement, and you can see the methyl group here is quite large here and large here relative to the hydrogens. And the bonds, all of the bonds from the front carbon to the back carbon are 60 degrees apart in angle if you were to project that. Okay, so notice here, it's not lined up exactly here, and this one's not lined up, it's in between. Okay? Well, what happens now if we take this butane molecule from that conformation and then start rotating one of the carbons relative to the other? Oops, that's not what I want to do. So here, for example, we take this anti-staggered conformation of butane, again, looking at the two and down the bond between the carbon 2 and carbon 3, and you start to rotate the front carbon to the right. What happens is that the CH3 here now starts to align and eclipse with the hydrogen in the back. And here, the CH3 from the back is aligning or eclipsing with a hydrogen in the front, right? Here are the sort of sawhorse picture. You can see they're 0 degrees apart from front to back. Here's the Newman projection picture of that, where they're lined up. What would you expect to be the difference in energy? Well, we've increased strain, torsional and some steric strain. So we go up in energy, and in this case, it's a little bit higher in energy than what we saw with ethane. All right, because we're not talking about just hydrogens. We're talking about now these methyl groups. So instead of 2.9 kilocalories per mole higher in energy, it's more difference. It's higher in energy by about 3.8 kilocalories per mole. Okay. Here's the visualization in motion. Again, you can see now, and I want you to consider the size of that methyl group. Now these are aligning in this particular eclipse conformation. All right. So as we continue rotating, then you get to another conformation where the bonds are staggered with each other. Again, each bond from the front to the back are 60 degrees apart. But this is different than the first one we had. Okay? In the first structure we looked at, the methyl group on the back was 180 degrees apart from the methyl group in the front. But this is not the case now in this particular position. Yes, we have relieved torsional strain by going from this eclipsed conformation now to the staggered conformation, but those methyl groups are coming closer together. So you wouldn't expect this conformation to be as low in energy as the original one where the two methyl groups were 180 degrees apart, right? And when I show you the more space-filling model, you'll see how they do start to bump into each other. So although it's less in energy than this eclipsed one, remember from our original anti-structure, this was 3.8 kilocalories per mole higher. This one, as we go staggered, you relieve some of that torsion, it goes down, but it's still almost a kilocalorie per mole higher in energy than the anti-conformation. Here's another term for you. Lots of terms when we talk about these. When we have the staggered conformation, that where these groups are coming closer together rather than being on opposite sides, this is referred to as the gauche butane conformation, or the gauche staggered. It's still staggered, but gauche meaning these groups are coming closer together. Okay. So look at this molecule now in 3 dimensions. You can even see in this picture as it rotates around how much closer those methyl groups are to each other. And you can see as this turns around here that those hydrogens are really coming close. The hydrogens from the back methyl to the front methyl now are starting to bump into each other. Okay? That's the increased energy of this versus the anti-staggered conformation. Okay? And this is mostly steric strain now, the strain of large groups coming close in space and bumping into each other. And then you keep going again, you get to this eclipse conformation again. So from the gauche staggered conformation, rotate by another 60 degrees, we get to our highest energy state. Now, we have an eclipse conformation where the CH3 group on the front is aligned 0 degrees apart from the CH3 group on the back. So in going from this conformation to this conformation, we've increased the torsional strain because all the bonds are eclipsed. And now we've increased the steric strain a lot because we've put this molecule in a conformation where the large groups are closest to each other. And you can see that here. See how close those methyl groups are in these conformations. So it's no wonder that this is going to be the highest in energy. So notice, particularly in this space-filling model, there really is very little room at all between those two methyl groups. Okay? So that conformation overall, and the reason why we look at these conformational analyses of molecules and look at all the different possibilities is, overall we know at room temperature this is spinning around rapidly. But if you get to an energy state at a particular temperature where that slows down and what you have is a less population of conformations of a molecule which are higher in energy than lower energy conformations. So it's important to recognize that even though these, all these conformations are existing, that's not necessarily the case at all temperatures. Especially as your energy difference gets higher and higher and higher, you could reach a point where the energy difference is so great that even at room temperature, only one conformation of the molecule dominates. And that's important to understand that for the reactivity of molecules. Okay, so this is now the overall picture of what I've just been talking about for butane, analyzing that bond between C2 and C3 and the energy profile. So notice here, all of the conformations I talked about, this is the anti-staggered, this is the eclipsed, this is the gauche staggered, sorry, my drawing's real small here, and this is the higher energy eclipsed. Okay, and that's the last conformation I showed you, but if you continue around the other 180 degrees around the circle, right, you essentially get a mirroring of that. You get to a, and I should have flipped that, sorry. I should have flipped this over here. If I'm really going to continue. You see you get the same, you get conformations which are identical in energy to the ones on the left. And that's why you see this symmetrical energy diagram. So if you take a look at this energy diagram, this is reflected here. Our anti is the lowest energy state, and as you start to eclipse the bond, torsional strain goes up. So you increase in energy. Okay? As that continues to rotate, and you relieve some of that torsional strain, that electron repulsion, you go down in energy. But because we have this steric strain of the two groups coming closer together, we don't go all the way down back to our 0 point from where we started. This is a little bit higher in energy than where we started, about 0.9 kilocalories. Okay? And as you go up, rotate further, then you start to really get that sterically crowded situation where the two methyl groups are next to each other. That's the highest energy, and so on. So that is how all of those things are aligned here. Okay? So what do you think this would look like if we had propane? What would that energy graph look like if we were looking at propane instead of butane? Let me just pull up let me see if I can pull up a word background here. Oops. Okay. Think about propane for a moment. What would, it only has two carbon-carbon sigma bonds. You have C1 to C2 or C2 to C3. So it doesn't really matter which we look at. If you take a look at propane, I'll just draw the sawhorse here. Okay. And then we have one carbon, two carbons, and then another carbon, CH3. Okay? So again, if you visualize this, ooh, it's hanging off a little. If you visualize this from that angle down the CC bond, what do you see? You see in a Newman projection, you see hydrogen straight down, hydrogen to the left, and hydrogen up to the right. And on the back, you see a CH3, hydrogen, and hydrogen. So I will ask this, do you feel comfortable being able to take that structure and draw the Newman projection of that and put all the groups on? You should be able to do that. That I would expect you to be able to know what positions are where from this structure to that structure. Okay, so I've drawn, and this is just habit, I usually start by drawing a staggered position because that's usually a lowest energy position or a lower energy position. Okay, so if I just think about then energy graph, okay, and I start here, I start at some 0 point on the energy graph, my starting point. And now as I rotate, what happens to the energy of the molecule? It goes up. So if I rotate this to an eclipsed position, sometimes it's hard to draw that. Okay, energy goes up. So I would get to an eclipsed position. And just arbitrarily, I'll just say that much energy. Should be a little higher than ethane. Okay, and then as I continue rotating, what happens? It'll go back down. And it goes back down to the same level. Okay? Because, and here's the key, and if I continue going around, it'll look just like the energy profile for ethane, except the energy difference is a little bit higher in each of those peaks than ethane. Okay? And it's because if I take a look at this molecule, it doesn't really matter. These three groups on one of the carbons we're looking at are all identical. So each of the three eclipse positions and each of the three staggered as you go around a full circle are going to be identical. There's not a difference like there is in butane, where you have a methyl group which is swinging around close to another one. So although there's a little bit more strain energy here, which increases relative to ethane, each of these relative to each other are the same. Okay? All right. It worked like that. Great. Okay. Well, just to remind you, I talked about a couple new terms here. When we have groups that are differently substituted on either end of the molecule that we're looking at, the bond we're looking at, if they're 180 degrees apart in the staggered conformation, that's the anti-conformation. And if they are getting closer together but still staggered, 60 degrees apart, we refer to that as the gauche conformation. And sometimes you'll hear me say that a gauche interaction. I'm talking about an interaction between bonds which are 60 degrees apart. Okay, not 180 degrees apart. Okay, well, one consequence of this, as we look at that, we can see as a bond rotates, that energy of the molecule goes up or down. It's oscillating back and forth a little bit. What that tells us, though, is that when we think about alkanes, which are longer chain alkanes, the energy of the molecule, the lowest energy state, or the lowest energy conformation, is going to be the one which is completely staggered, right? So we minimize as much as possible any electron repulsion between bonds on adjacent carbons. And anything that might have a gauche interaction or anti-interaction, all the bonds possible that would orient anti are anti. So for example, this is why we tend to draw linear alkanes out just by habit in this sort of bent linear fashion here, where everything is like a fully elongated chain, right? That reflects the lowest energy conformation. So you can pick any carbon-carbon bond on here that's not on the end of the molecule. So for example, this carbon-carbon bond, right? If you look at that carbon-carbon bond, this group and this group are, from this carbon to that carbon, are 180 degrees apart if you were to line them up in that Newton projection, right? If you take a look at this carbon-carbon bond, this group and this group are 180 degrees apart, or anti. Okay, and you can do that all the way up down the line. So this fully extended way to draw is the lowest energy. So if you look at something like the comparison here on the bottom, the molecule certainly could rotate and twist up. This one, if you were to analyze that conformation frozen in time, this would be higher energy than this one on the right. Okay? And that's because what you see is that this group, if we analyze this particular bond, right, this group and this group are coming close together. That's going to be higher energy than the fully anti, fully open linear chain of the molecule. Okay? So any questions on the examples I've given so far for ethane, propane, butane, or these molecules? It gets a little more complicated because we know that organic molecules and carbon-based molecules can also form rings. And rings do certain things to the molecule to constrain it, right? So if you have a linear chain, alkane, all of the single bonds can freely rotate. But if you tie the ends together, right, now it can no longer rotate. Okay, because it's a ring structure. You can't rotate all the way around. You have to break the ring open in order to rotate the bond all the way around. So while ring compounds, if they're large enough, can certainly move, the bonds can rotate a little, they can't rotate in 360-degree circles. Okay? And the other thing about cycloalkanes is that because of the constraint of the ring, it forces the molecules into conformations where there might be additional torsional strain or additional steric strain, or what we refer to as angle strain. And so when we look at cyclic alkanes versus open chain alkanes, we see additional energy in the molecule due to that, being forced into specific conformations. So some more definitions to refer to that. We have this overall word which we refer to as ring strain. That's actually made up of the combination of those things that are imparted due to the ring. One is that if the ring is restricted in size, when bond angles, of course we know a tetrahedral bond angle prefers to be ideally 109.5 degrees, right? So if you have a cyclic molecule which actually forces the bond angles to be smaller than that, or potentially a cyclic molecule which forces the bonds to be larger than that, that is a higher energy angle between those atoms. And this I'm talking about angle from 1, 2, 3 atoms in a row. And we see both of those cases. And that's referred to as angle strain. Torsional strain, because something isn't freely rotating, it might be fixed in space where you always have eclipsing bonds or near eclipsing bonds. Then rings can impart additional torsional strain. And because of the ring, you might be forcing groups to come closer together. So all those things added together that are in addition to the energy of the molecule if it were an open linear chain is what we refer to as ring strain. Okay, we can see that. We can compare the difference in energy for a molecule, additional energy for the molecule relative to that molecule if it were not a ring, by comparing the heat of combustion. Okay. We talked about that as a way to measure various relative energies. So this is just it's not very quantified well and probably not to scale, but gives you an overall view of how the size of a ring, how many numbers of carbons in the ring, impact the strain energy of the additional strain of the ring by the heat of combustion. So if you look at this, if you have a ring, the smallest possible ring is made up of 3 atoms. So cyclopropane. This molecule actually has the highest amount of ring strain of any of the cycloalkanes. Okay, we'll take a look at why. It has very severe angle strain, it has severe torsional strain, and if you start to put additional groups on, you have severe steric strain. Okay, but if you compare, if this 0 point energy here is the open chain 3-carbon group, by taking a C3 compound and tying it in a ring, you introduce a great deal of additional energy into the molecule. Okay, that's what this chart is telling you. As you go from a 3-membered ring to a 4-membered ring, a 4-membered ring is slightly less ring strain associated with it, slightly less additional energy. That drops off dramatically, that additional ring strain energy, when you go to a 5-membered ring. And a 6-membered ring is the lowest energy. There is really no additional strain imparted into a molecule due to the ring of a 6-membered ring. There are some cases where when you start substituting it, there's additional steric, but in terms of torsional strain and angle strain, a 6-membered ring is as good as it can get. Notice though, if you go a little bit higher ring size, you reach a point, you start to go up a little bit in ring strain, and that's because not every bond can be staggered anymore until you get to a large enough ring that it basically mimics a linear alkane. If a ring gets large enough, then there's enough flexibility in it that it can relieve all torsional strain and steric strain and angle strain. So anything really above like a 14-membered ring, there is no additional ring strain generally in those molecules. Okay, so let's take a little bit closer look at cyclopropane. Cyclopropane is a 3-carbon ring, right? And if you just look at that, right, geometrically that would be a triangle. And the angle, the bond angle of a triangle is 60 degrees. Okay, what's the preferred angle for an sp3 carbon? An sp3 carbon wants to be 109.5, roughly, right? So, that's very, very far away. 60 degrees is very, very far away from the preferred angle. As a matter of fact, this is such a small angle between the carbon here and the carbon here and the carbon here that the bonds don't even overlap. So if you look at the sp3 orbitals, which actually overlap to form the covalent bond, they don't actually line in the perfect shape along that line to get that perfect end-to-end overlap. In cyclopropane, those orbitals are actually bent. That's what I've indicated here in yellow. The covalent bonds are not straight bonds. So even the bonds are strained so much in cyclopropane. So it's no wonder cyclopropane has such a high energy, right? Well, imparted by forcing it into this ring. Okay, here's a picture view of that. Gives you a little bit better perspective on that. Notice also in cyclopropane that since all three of these carbons lie on the same plane, because 3 points define a plane, there's no way for this molecule to, there's actually no rotation about any of these bonds. And notice what happens is that the CH here is eclipsed with the CH here, and then here. So if you look down any bond, for example, if you look down this carbon-carbon bond here, you will see from this carbon front to this carbon back that there's 0 degrees between those CH bonds. Okay, they are completely eclipsed. There's no movement possible in the molecule, and so you can imagine that the energy of the molecule is going to be the highest. Okay? You see that? Hopefully these three-dimensional pictures give you some better perspective on that. As we start to substitute groups on, you can see that steric strain will also be very, very important. Okay, any questions on propane? Okay, I want to stop here today and take a quiz. I'm going to stop this right now. We're going to take a quiz, and feel free to use your notes. I don't care. What I just ask is that you do the answers yourself and don't use your neighbor's answers.